So sodium was +1, metal, non-metal, they form ionic compounds. Phosphorus is in group 5, so it has a charge of -1, -3.
Yes.
So the formula is what?
Na3P.
Okay, so it's going to be Na3P, right? And I told you that the name of the of an ionic compound, okay, whenever you have an ionic compound, what happens to the name is that the sodium name remains the same. Phosphorus, instead of calling it phosphorus, a negative ion of an element has a suffix which is "ide." So instead of being phosphorus, it's going to be actually phosphide. It's going to be IDE. Then you've got magnesium and sulfur. Mg is in group 2, so that's +2, and sulfur is group 6, so that's -2. So the formula is going to be, you don't need to do crisscross if the charges are the same. One thing about crisscross is that it has to be the simplest ratio. Like even if I crisscross and I get 2 and 2, if I do crisscross and I bring this 2 over here and this 2 over here, the charges, the ratio of the ions, it has to be the simplest ratio. So if you're getting 2:2, it's automatically going to be simplified to 1:1. So it's going to be Mg1 and S1, and that's going to be called magnesium. It's magnesium and sulfur, but the sulfur suffix would change. Instead, it would be called sulfide. So I'm just going to do one more, which is, let's do aluminium and sulfur. Aluminium is group 3, so that's +3. And sulfur is -2. So it's going to be Al2, and S is going to be 3. So this would be called aluminium and sulfide. So the thing is that you've got ionic compounds. We did dot and cross diagrams. I explained to you that metals, they like to lose electrons, and non-metals, they like to gain electrons, and that ends up in the formation of an ionic compound. Now what we're going to talk about very, very quickly and very briefly, just for a quick revision, and that is the structure of an ionic compound. Like, we are discussing their formulas, so we're going to quickly go over the structures of ionic compounds. And there would always be compounds, because an ionic compound is always formed when two different things, one of them is a metal and the other one is a non-metal. One of them loses electrons, the other one ends up gaining electrons. So the structure of an ionic compound is that it has a giant ionic lattice. Yes. So it's a giant structure. So when I say that that there is NaCl, like I've got NaCl, Na is +1 and Cl is -1, and it's also crystalline. So they tend to form crystals. So when I say that the formula of Na, like if I talk about NaCl and I use the word or write this formula NaCl, what I'm basically referring to is a giant ionic lattice. I'm just going to show you the image of what this giant ionic lattice looks like. So it's this thing over here. So let me just copy this and bring this image over here. So the thing is that there would be many ionic bonds in a giant ionic lattice. There would be not just one Na. Like the formula is going to tell you that there's one Na and one Cl. Remember, the formula of an ionic compound, it doesn't tell you the actual number. It tells you the ratio of, this is known as a formula unit. Okay? Ionic formulas are known as formula units. So it doesn't tell you that there's going to be just one Na and one Cl. What it tells you is the ratio of the ions. That is the information that you get. So in an actual lattice, you might have, let's say, 50 sodium ions, and there might be 50 Cl ions.
In one atom?
In one lattice. I mean, the lattice is a giant lattice. Like you'll have one sodium ion, one Cl ion, one sodium ion, one Cl ion. So it's going to be an endless structure. It's going to be a giant structure. You could have small crystals, you could have large crystals. You can have really big crystals. For example, there could be 1 million sodium ions in a lattice. And there could be 1 million Cl ions also present in the same lattice. Okay, so remember this, that the formula of the Ionic lattice, it doesn't give you that information that how many sodium ions and how many Cl ions you've got. The only information that it gives is that it gives you the ratio of the ions in the lattice. It's going to be a network, a giant structure of positive and negative ions. They're all attracted to. So it's going to be a regular arrangement of oppositely charged ions, of positive and negative ions. And they would be alternatingly arranged. There's going to be a positive ion that would be attached to a negative ion, which would be then attracted to a positive ion, and so on. So remember what the formula tells you. Like all the formulas that we made over here, for example, Al2, for example, this one, Na3P, the information that this formula is giving us is not that the lattice is going to have 3 sodium ions and there's going to be just 1 phosphorus ion. The information it gives you is the ratio. Like the actual lattice might have 3000 sodium ions, and the ratio of the phosphide ions would be 1000 according to the ratio that's given in the formula. So the actual lattice would be really big. It's going to have lots and lots of positive and negative ions. And the formula is going to tell you the ratio in which they're going to exist. Is this point clear?
Yes.
Now, the other things about these ionic compounds, TK. Unlike covalent molecules, like if I say carbon dioxide, in a covalent molecule, the number of atoms that's described in the formula, that's the actual number. A carbon dioxide molecule actually just has 1 carbon and it's got 2 oxygen. That's it. TK, in a covalent molecule, that's not the ratio. That's the actual number. In ionic compounds, this is not the actual number. This is just the ratio. The number could be really big or it could be really small. So which is why these are not called formula. They're called formula units. Now, some properties of these ionic lattices. Remember, it's going to be, I mean, this could be a tiny crystal of NaCl. I mean, most of them are going to form crystals. So this is one example of a crystal that's existing. You could have large crystals. You could have really small crystals as well. The first thing is, can anyone tell me, do they have high melting and boiling points or low melting and boiling points? The first one. Anyone? Is there any idea?
I think it's low.
Look at the attraction. Is it going to be very hard? I mean, they're very strongly attracted to each other. I mean, the positive ions are attracted to the negative ions are attracted to the positive ions. So there's a lot of attraction between them. So it would be really hard to actually melt them. Like if you want this ion to, or change them into gas, the boiling points would be low. Like the other negative ions around it are strongly pulling this positive ion. So it would be very hard for the positive ion to turn into gas or escape as a gas or be able to move around. This positive ion is stuck in the middle. It can't move around in liquid state, or it can't escape freely and start moving freely as in gaseous state. So is this point clear?
Yes.
Yes.
Okay, Ahmed, is this clear?
Yes, sir.
Yes, sir.
Achha, so the first thing is they've got really, really high, not really high, they've got high melting and boiling points in a relative sense compared to all the other substances. They've got high melting and boiling points, and they're mostly solids. And the reasons why they're having high melting and boiling points is that there is strong attraction between positive and negative ions. One of the factors is the attraction is strong. TKBW is between positive and negative ions.
For ionic compounds, right? Or only for NaCl?
For any ionic compound, TK, I mean, that applies to NaCl as well, right? I mean, I'll show you the lattice if I can figure out the lattice of let's talk about aluminium oxide. That's also an ionic compound. I mean, for example, this one. I mean, that's also NaCl. Forget this. Aluminium oxide is going to have a pretty similar lattice, except that the arrangement would be not as regular or similar to NaCl. I mean, for example, if there's a better diagram, just a second. Let's go with this. Just 1 second. So they're not showing this, but this is Al3 plus. This is O2 minus 1 ion. So Al3 plus is attracted to O2 minus. O2 minus is attracted to Al3 plus, which is attracted to O2 minus. So positive and negative ions, they're all attracted to each other. So, I mean, the diagram is not, I mean, it's going to be very similar to this one, except the ions will be attracted to each other because they have different numbers now. It's Al2O3. So for every 2 aluminium ions, there's going to be 3 oxide ions. You don't have to go into that much detail, but what you just need to know is that the lattice would be kind of similar to this one, but not exactly similar. The arrangement would be kind of slightly more haphazard, but it would look kind of similar to this. Is this point clear?
Yes.
So there's going to be strong attraction between, so one of the reasons why they've got high melting and boiling points is that the positive ion, that's, I mean, if you can, I mean, this one is attracted to negative ions. Plus, it's not just attracted to one negative ions, it's surrounded by negative ions, and the negative ions are surrounded by positive ions. So it's a giant, the other reason it's a giant structure, and it's got many ionic bonds.
Yes.
I mean, this force of attraction is known as the ionic bond. Now, very quickly moving forward, so that the first thing is settled, that they're really strong. They've got strong attraction. Can anyone tell me, apart from NaCl, what is the everyday ionic compounds that you see around you? I mean, NaCl is one of them. Any other one, if you know of? Anyone, any idea? Yeah, I can't hear you properly. So I'll tell you, just around you. Marble, that's an ionic compound, right? Cement and concrete to an extent. I mean, they've got other things mixed in them, but they're kind of similar to an ionic compound, or they have portions. I mean, they're mainly the bonding part, the attraction part, that's ionic. I mean, obviously add mix other things to it. You add sand to it, you add rocks to it, which are definitely not ionic. But cement, the binding thing, that is ionic. So these are some of the things that you see. A lot of ceramics around you are ionic. Ceramics are those things. I'm going to talk about ceramics in a bit, just very quickly. So marble, etc. These are ionic compounds. These are ionic lattices. So the first thing is, some of them are really strong. Like concrete is really, really strong. That's a pretty tough ionic compound. It's extremely strong. You can't say that for NaCl. NaCl is not that strong. You can even crush it with your hands, right? That's not that strong. So the thing is that even between ionic compounds, some ionic compounds are really strong, their lattices are really strong, and others are not that strong. So what determines strength of the ionic lattice? That's a question. So the strength of ionic lattice, that's a big question mark. So I'll have two ionic compounds with me. I've got NaCl. Na is +1, the one that we just drew. It's attracted to Cl -1. Cl -1 is attracted to Na +1. So imagine them as circular atoms or ions. So all of them are attracted to each other, and the attraction continues in 3 dimensions. So Na +1 is attracted to Cl -1, and it just keeps on going. And I've got another ionic compound. This one is MgO. Mg is in group 2, so that's 2 plus. O is 2 minus. The O2 minus is again attracted to Mg2 plus, which is then again attracted to O2 minus, which is then again attracted to Mg2 plus. So the lattice continues. Okay, there's a positive ion, there's a negative ion, they're all attracted to each other. So I'm just drawing portions of those lattices, okay? Something similar to this, the one that's drawn or sketched over here. Okay, positive and negative ions all tightly attracted to each other. Now, can you tell me which one out of the two will have a stronger attraction? Would it be NaCl or would it be MgO? And what does the attraction depend on?
MgO.
Okay, MgO is going to be stronger. Okay, there's going to be stronger attraction. What's the reason for that?
More molecules, better. I mean,
No, you don't call them
more
molecules.
electrons.
I mean, never call them molecules first thing. They're ions, okay? So they are ions. What's the other point?
The electrons, more electrons are bonded together.
No, it's not more. I mean, more electrons are. The thing is, why is there attraction? A positive ion attracts a negative ion, right? So what you have is you've got a positive ion, which is Mg, and you've got a negative ion. So the attraction is because of the charge. There's +2 and there's -2. So greater charge, I mean, there's greater charge. Over here, the charge is lesser. Like you have Na+1 and you have Cl -1. So +1 and -1, the positive charge is not that large. The negative charge over here is not that large. So the attraction is going to be weaker. Opposite charges, they attract. Opposite charges attract over here as well, but the opposite charges are greater in quantity. You've got +2 and you've got -2. Is this point clear?
Higher charge is more strength.
So the first factor is, if you've got greater charge on ion, Mars, is this clear? Sidra, is this clear?
Yes, sir.
I say if you've got greater charge on ion, there's going to be stronger attraction. Okay, that's, I mean, there's no doubt about it. For example, if I have another lattice where the charges are even higher, the attraction would be even stronger, like aluminium oxide. Aluminium is +3, oxygen is 2 minus. So the attraction between these two ions is going to be even stronger. Like they're going to form a lattice and a 3-dimensional lattice, and there would be other ions as well, +3 attracting a -2. But you've got even greater charges, so the attraction between the ions in the lattice is going to be even stronger. So that's the first point. Greater charge on the ion leads to stronger attraction. The second factor is smaller. It's about the size of the ions as well. Smaller ions are more tightly packed. Like if you look at this lattice over here, if you had a smaller atom and it was forming an ion, the ions would be more tightly packed. They would be closer together. If you've got a bigger ion, the ions would be further away from each other and they will be far away from each other. So that's another factor, that if you have smaller ions, they are going to be closer together in the ionic lattice. So in the and there's going to be stronger attraction because of that. And that's a universal fact. Like whenever bonds are formed, the smaller the ion, the closer they're going to be to each other. So the attraction would be a lot stronger. Is this point clear?
Yes.
So strength of an ionic compound depends on two things. One is how big is the charge? This is +1, this is -1. The charge isn't big enough, so the attraction is going to be weaker. The second factor is, over here the charge is much bigger, so the attraction between the ions is going to be a lot more. So the ions would be attracted to each other very strongly. Over here, the ions would be attracted to each other even more strongly. The other factor is the size of the ions. How do you figure out the size of the ions? That's an easy part. Like if I open the periodic table, now that's your easy part, how to figure out the size. Let me just turn this around. So if you look at the size, the elements on the top, the ions that are on the top, they would always be smaller because they just have very few electrons. Like if fluorine is forming an ion, it's got 9 electrons. It's going to be really, really tiny. If iodine is forming an ion, it's going to be much bigger in size. It's going to have a lot of shells, and it will have a total of 53 electrons. So as you go down the periodic table, the size of the atom or the ion, it keeps on increasing. So if the element is at the top, it has a small ion. If the element is at the bottom, it's going to have a bigger ion. So for example, let's do a few comparisons. Who's going to form a stronger ionic bond? I've got NaCl versus KCl. Now, both of them have similar charges, like Na is +1, Cl is -1. Over here, you've got K is +1 and Cl is -1. So they're both kind of having the same charges. The only difference is that Na and K, that's the difference. Like if you look at the periodic table, Na comes above K. So Na is smaller in size. K over here is bigger in size. Okay, if you look over here, Na is bigger. Sorry, Na is smaller. And K has a lot more electrons. It's bigger in size. When you move down the group, so K has a bigger ion. So that means the ions are not tightly packed and they're not close enough. So the attraction would be weaker. This one is smaller ion. So this one will be a stronger lattice compared to KCl. Is this point clear?
Yes.
Okay.
Yes.
So just remember, focus on the charge or the size. That will give you an idea of whether the lattice is going to be strong or whether it's going to be weak. So a lot of ionic lattices, they can be kind of weak, like NaCl is weak. You can crush it with your hands. Or MgO. MgO is really, really strong. And MgO is as strong as probably diamond. Like if you look at the melting points of magnesium oxide, so magnesium oxide has a really high, it's very hard for the ions to move around. So magnesium oxide melting point is kind of in the same range as diamond. 1 second. So the melting point of magnesium is like close to 3000 degrees centigrade. Aluminium oxide is kind of really high as well. Sodium has +1, so its melting point decreases. Like it's not that strong because Na is +1. So since Na is +1, the attraction between the oxygen ion, which is -2, that's going to be lesser. Calcium oxide is stronger because calcium is +2 and oxygen is -2. So the charges are greater. So there's going to be more attraction. So some ionic compounds are really, really strong, like magnesium oxide. You can have compare it with diamond. Diamond is kind of considered to be it's considered one of the strongest substances. So that's around 4000, and MgO is kind of around 3000. So you can see that some ionic lattices can be really, really strong.
Yes.
TK, is this clear?
Yes.
Yes.
So then there's another term that's used, and I had used that previously, and that was ceramics. I told you ceramics are ionic compounds. So what are ceramics? I'll just give you a brief idea of what ceramics are. Some substances that are very strong, and they've got very high melting points. Which means that they're really tough substances. I mean, you can use them in extreme conditions. Those are known as ceramics. It's not specific to ionic compounds. Any substance could be ceramic if it follows this property that it's really strong and it's got really high melting points. So a lot of ionic compounds can be really strong. One of the examples are MgO and Al2O3 are often, because they're so strong, NaCl doesn't fit this property. Like NaCl, that's not very strong. You can crush it with your hands. So that's like an ionic compound that's not really strong. So only some ionic compounds would be classified as ceramics. Ceramics are substances that are really, really tough. So MgO and Al2O3 are often used as ceramics. So where do you use ceramics? Ceramics are used in for making furnaces. Like extreme conditions, you need really, really tough substances for making furnaces. I mean, your oven trays are made from ceramics. Sorry, the trays that go into your oven, they made out of ceramics. Your dishes, etc., which you need to heat in the microwave, they're made from ceramics. They need to be tough. They need to have. They need to be strong, and they need to have very high melting points. Electricity transmission. You need devices, not for electricity transmission, but electricity holders, etc. Or device covers. They are made from ceramics. I mean, I'll give you an example for that.
Ceramic.
Hmm?
Can they use a diamond as a ceramic?
No, they can obviously use diamond as a ceramic. It's the only thing is it's going to be very expensive. So that's why they don't use that. Okay. I mean, diamond fits this property. Okay. Anything that's really strong, anything that has really high melting points, that is a ceramic. Okay. I mean, concrete is, you can consider concrete as ceramic. It's because it's really tough. It's very strong. It's got high melting points, right? Marble can be considered a ceramic, but marble is not that strong. Like it can break. Okay. So space shuttle, space probes, like if there's a space probe that's landing on another planet, it heats up when it passes through the atmosphere. So the outer covering is made out of ceramics. For example, if I can show you a space shuttle, I don't know, its heat shields were once made from ceramics. So, for example, I mean, look at the tiles over here. TK, for example, this is your space shuttle. It heats up when it enters the Earth's atmosphere. So the body of the space shuttle is covered with tiles. These are tiles. These are like marble tiles. They're made from ceramics. These are made from ionic compounds. These must be very advanced substances, but they would be similar to ionic compounds. Tiles that surround them so that the space shuttle doesn't heat up. Okay, so it's covered by these tiles. And so is your, like if you make furnaces, it will be covered with MgO tiles. So I don't think, I mean, this is magnesium oxide. It's a brick. It's like a brick. So your big furnaces, really, really big furnaces, they have these brick lining. I mean, this one shows this, I think. The furnace is lined with MgO bricks. Okay, so to protect it, because MgO is really tough and it's got a very high melting point. So that's going to save it. You can't use NaCl because NaCl is weak. Okay, so remember what ceramics are. I mean, ceramics could be not just ionic compounds, they could be any compound as long as it's tough, as long as it's really strong. Is this point clear?
Yes, yes.
So now another thing about ionic structures is that they're kind of brittle. I mean, at one instance, they're really strong. Like concrete is really, really strong, but they have this problem that ionic compounds are also brittle. What that means is, what does brittle mean? Brittle means that, let's say I have a slab of concrete. I mean, or maybe I have a piece of tile, right? I mean, you make floors out of this tile, right? So let's say this is a tile, a marble tile, that's an ionic compound. The positive and negative ions are all strongly attracted to each other. I mean, the structure of the tile is similar to this one. It's got loads of positive ions, loads of negative ions, all tightly attracted to each other. So that's what your marble tile is. And it's kind of tough. It's like we are walking on it. I mean, cars drive on it. So that means it's pretty tough. But the problem is that even though it's tough, but beyond a certain point, if you apply a force, like if I start hammering it over here, I start hammering it at this point. What happens is that it doesn't just break at this point. The whole tile kind of cracks up. I mean, there's going to be cracks. It's going to crack up and into small, tiny pieces. So it's also brittle at the same time. So it can be really tough. It can absorb a lot of forces, but beyond a certain point, the whole thing the whole structure kind of collapses. Is this clear? Do you understand this point?
Yes.
The same as with concrete. Like you can make really, really large buildings out of concrete, but the whole building can collapse in one instance. Like if an earthquake comes and the force is strong enough, the whole building will just shatter into tiny, tiny pieces. So that is what brittle is. Now the question is, why are they brittle? And the answer to that is that ionic compounds are really tough. Like positive and negative ions are really strongly attracted to each other. But ionic lattices are very sensitive to the arrangement. So for example, I've got an NaCl structure. Although NaCl is not that strong, NaCl is brittle as well. Like you have a salt crystal and you crush it, it breaks into tiny pieces, right? So what's wrong with the lattice? Na+1 attracting Cl-1, which is attracting Na+1, which is then attracting. So let's say this is this tiny lattice. And I've told you that they are very sensitive to the arrangement. The arrangement of the ions should not change at all. Okay, so they're going to tightly attract each other. They will all attract each other very strongly. They won't allow anyone to move around. The sodium ion will be attracted to the Cl ions. The Cl ions will be attracted. So they're all attracted to each other. So beyond a certain point, if you apply a force, the ions will not move. They're going to resist. Just like your marble tile or your concrete, it's going to absorb the force. The ions will not be able to slip. The Cl ion is holding the sodium ion in place. The Cl ion is being held by the sodium ion over here. They're all attracted to each other. Is this point clear?
Yes.
Right. So they're able to withstand forces. But if the force exceeds a certain point, and all of a sudden you applied so much force, like you have a concrete beam and you applied, now that's a very strong concrete beam. You've got a big tower, it's a strong concrete beam, and there's an earthquake. And all of a sudden, a few of the ions, they kind of slip because of the force. You've applied too much force, right? Is this point clear?
Yes.
So you need to apply a lot of force for the ions to slip. But once the ions have slipped, what do you have over here? You've got a positive ion and you've got a positive ion next to each other. What would happen now? Will they attract or will they repel?
They repel.
So they're going to repel. So that means, and you've got two negative ions together now. So they're going to repel each other as well. So all of a sudden a crack would emerge and the whole structure would collapse, because now all of a sudden you've got positive ions next to other positive ions, and that shouldn't have happened. So all of a sudden they start repelling, and so it starts breaking up into pieces. And that's what happens to the marble tile as well. Beyond a certain point, you keep on applying a force, the ions don't move. But if you hammer it too strongly, if the ions move a little bit, the whole thing would crack up. It will just shatter into pieces. Is this clear?
Yes.
Okay, is this clear to everyone? Ahmed, is this clear as well?
Yes, sir.
Raeed, is this clear?
Yes, sir.
So they're brittle at the same time. Okay, so that's one thing. So even the strongest of concrete, the strongest pieces of marbles, they end up getting shattered if you apply too much force. So that's ionic compounds. I said we're not done with ionic lattices. What we have done is at the moment is we studied. So let's do a few more properties and finish ionic compounds for a second. What are the other properties that they conduct electricity? But they're only able to conduct electricity if the ions move around. So that's another property. Property number 3. That is ionic lattices they conduct. And remember, you either refer to ionic compounds as lattice or refer them as compounds. Never ever call them molecules.
Yes.
So ionic lattices conduct electricity when they are molten or aqueous. When they're molten or when they are aqueous. Because the ions will be able to move around in molten state. Like you've got sodium ion and CN, but to melt it, you would have to give it a lot of energy. So if you have a lattice of sodium ions and Cl ions, in solid state, the ions will not be able to move around. The ion has to be really energetic and then it will be able to move around. So they already have very high melting points. So in molten or aqueous state, you've got free moving ions or free moving charged particles. Because electricity is the movement of charged particles.
Yes.
No electricity conduction happens in solid state. In solid state, the ions are stuck in place. So there would be no movement of charges, no movement of ions. So this one, solid state, the charges can't move, no electric conduction. If you melt them, if you give them sufficient energy, if you dissolve them in water, we're going to talk about dissolving in water in detail tomorrow. If you dissolve them in water, that's when they start conducting electricity because the ions will be able to move around. Okay, so that's the third point. The fourth one is about solubility. We're going to discuss solubility in a lot more detail in the next class then. Okay. Is this clear? Any questions about this?
No. No.
Let's continue. I'll just quickly wrap up ionic compounds. I'm more interested in formulas and equations so that we can start doing moles and past paper questions related to moles, AS moles. So we'll just quickly go over ionic compounds very, very quickly. Take care after this. So, okay, everyone, take care.
Okay.
Hafiz.
सर
हाँ जी.
सर आप ये जो है आज की क्लास YouTube पे आप अपलोड कर सकते हैं फिर मतलब लिंक सेंड कर सकते हैं आप इस रिकॉर्डिंग की.
हाँ, लिंक में सेंड कर देता हूँ. ठीक है.
सर ये जो बोर्ड की भी लिंक है ये भी सेंड कर दें.
बस ठीक है, मैं कर रहा
हूँ. ओके सर, थैंक यू.
और सर
हाँ जी, हाँ जी.
ये जो आप पढ़ा रहे हैं ये कौन सा चैप्टर 1 और 2 है या 3?
ये तो अभी बिल्कुल बेसिक है. मोल्स हमने करना है ना, तो इक्वेशंस कर रहे हैं ना उसकी.
मोल्स तो चैप्टर नंबर 3 है.
हाँ, तो मोल्स कर रहे हैं ना. ठीक है.
डायरेक्ट 3 से स्टार्ट.
वो क्योंकि ओ लेवल से उसका ताल्लुक है ना, उसमें कोई नई चीज तो पढ़नी नहीं है. ठीक है.
ओके सर,
ठीक है सर. अल्लाह हाफिज़.
ओके, लव.